Good morning, Mananda. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in today's lecture, we are going to learn about some of the prerequisites topics or related to the electromagnetic waves and transmission lines. So, in that, the first prerequisite related to the electromagnetic waves and transmission lines or introduction to coordinate systems. Then in this particular lecture, we are going to learn about what do you mean by coordinate system, in how many types of coordinate systems we are supposed to consider in the case of analysis of electromagnetic waves, and in each and every coordinate system case, what are the variables and how will all the coordinate system variables are arranged, then in the vector form representation, followed by the transformations from one type of coordinate system into another type of coordinate system, we will learn particularly in this lecture. Now, there are three prerequisites for electromagnetic waves and transmission lines. Those are, first one is vector algebra and coordinate systems, followed by vector calculus. So, in this particular, we will learn about vector algebra and followed by coordinate systems. So, in all the vector algebra case, we will discuss about what do you mean by vector and a scalar, then what are the different examples for scalars and vectors, then followed by how we will perform addition of a vector and subtraction of a vector. Then coming to the multiplication of a vector, there are two cases are to be considered in this scalar product as well as vector product. Then position vector and displacement vector are to be discussed in this particular vector algebra. Now coming to the coordinate systems, there are three cases of coordinate systems or occur. In that, the first type of coordinate system is a rectangular coordinate system. It is also called as Cartesian coordinate system. And second classification is cylindrical type of coordinate system. And coming to the third, it is spherical coordinate system. So coming to the vector algebra. So generally, a quantity can be measured in either a scalar or a vector. Scalar or a vector. As we know that scalar is a quantity which has only magnitude and vector is a quantity which has both magnitude and directions. So some of the examples for scalar which has only magnitudes means the mass, temperature, population, and all are examples. Electric potential, all are examples for scalar quantities. Coming to the vector quantity, displacement, electric field intensity, force, velocity, these are all examples for the vector quantities. Now coming to the scalar quantity and vector quantity, now if we have two vectors, we want to perform addition of the two vectors, then we are supposed to add those two vectors. And if we want to perform subtraction, we have to subtract one from the another one. So like that, in order to perform the addition and subtraction along with that multiplication of a vector quantities, first we have to represent how the vector form need to be represented in the equation or mathematical statement. So for that, I am using the notation for in order to represent the vector as A over bar. Why? Because vector quantity is a quantity which has both magnitude and direction. So that can be represented as here a bar is equal to, sometimes we used to represent it with ax, comma ay, comma az, or in other words, we can write it as ax, ax plus ay plus az. Right? So this is the way we can represent the vector form. In the point form representation have only all the magnitudes in the three directions, and unit vector representation case including all the magnitudes along with the unit vector directions in the respective x, y, z, means ax plus ay plus az. So this is the case. If we want to find the magnitude of this one, then modulus of a is equal to root of all the squares of the magnitudes in the x, y, z directions we have to consider. that is ax comma ay, sorry, ax square plus ay square plus az square. This is the way we can represent the magnitude of the unit vector. Magnitude of the given vector means this one. Suppose if we have a vector called a equal to ax plus ay plus az, then another vector called b, then that is given by here bx ax plus by ay plus bz az. Now, if you want to perform the addition or subtraction between these two, then we have to use a plus r minus b. Means a plus b is for addition and a minus b is for subtraction. So, to perform this one, a plus r minus b equal to, we will consider it as ax plus bx into ax plus ay plus by into ay plus az plus bz into az. Right? This is the way we have to perform addition of these two. Sometimes we used to consider subtraction, means that is the case we will consider as a plus r minus b, and all in place of plus we just consider all the negative terms. So this is the way, if we have two vectors a and b, then in order to perform addition and subtraction we use, this is the fundamental formula. Now, along with the addition and subtraction of a vectors, we'll have another term called vector multiplication. Vector multiplication. In order to multiply here, we'll have two different classifications. One is related to the scalar product, and second one is vector product, where this scalar product is also called as dot product, and vector product is also called as cross product. So, now to perform this scalar product or dot product, we need to multiply. See, the formula for that is given by here, scalar product, then a dot b, means vector a dot b is equal to mod a into mod b into cos theta a b. Right? If you want to find the angle between these two, then this can be written as cos theta AB equal to mod, AB equal to A bar dot B bar by mod A into mod B can be written for the angle. Similarly here, vector product or cross product can be written as here, then A bar cross B bar, which is equal to mod A into mod B into sine theta AB into AN is the vector form, right? So if you observe here, in the scalar product case, we'll have only magnitudes, and if you observe vector product or cross product case, then it is to be represented with a unit vector called AN bar. Now I want to define the unit vector as AN bar, or let it be A suffix A bar. So small a is a notation for unit vector, and A belongs to the given vector called A. And it is given by, sometimes we used to represent it with all the magnitudes, or sometimes with a vector form, means along with the magnitudes unit vectors also. So that can be given by here, A suffix A bar equal to, is defined as the ratio of the vector to its magnitude, is given by here unit vector, and generally it is to be written as A equal to ax plus ay plus az by magnitudes in all the directions, or given by ax square plus ay square plus az square. Right? So this is the way we can consider the unit vector in the a direction, as given by vector to the magnitude of that given vector is defined as unit vector, and it is represented with small a suffix a. Then along with this vector and scalar quantities, then addition, subtraction and multiplication of these two, will have the two vectors called, one is position vector and another one is displacement vector. Position vector and displacement vector. So in order to define this position vector, suppose a vector is represented at the origin. Now we want to locate at a point P, then here at a point Q is located, then the origin is placed as like this. Now here is the distance. Now from I want to find the distance from the origin to the point P where it is located at a particular point. So this distance is given by means OP bar and OQ bar are said to be position vectors. Means position vector is the vector and it is the this particular case we'll find the distance between two means it is the distance from the origin to the particular point P or origin to the point Q. Now suppose we want to find the distance between P and Q. P and Q are the two reference nodes, well-defined nodes. Then we want to find the distance between P and Q means that is the case that vector is said to be displacement vector. Means PQ bar can be written as means if the P point is located at x1, y1, z1 and Q is located at x2, y2, z2, then the distance between two can be written as here x2, y2, z2 minus x1, y1, z1. Okay. Now this is the case. We will write the formula as x2 minus x1 into ax plus y2 minus y1 into ay plus z2 minus z1 into az. And this is the case. This p bar q is said to be displacement vector. Right? So related to the vector algebra, these are all the fundamentals. Means firstly we have defined what do you mean by a vector and a scalar, and we have seen some of the examples for vectors as well as the scalars. And after that, how we'll define a vector in two different ways, as with only magnitudes case and along with the magnitudes, if we consider unit vectors, how we will represent the vector we have learnt. Then after that, how to find magnitude of the given vector also we have learned. That is modulus of A is equal to root over ax square plus ay square plus az square. Then instead of having a vector A, if we have two vectors and another vector called B, then A, in order to perform addition and subtraction between these two, then C equal to means if you add these two or if you subtract these two, the resultant vector will be given by here C bar is equal to A bar plus or minus B bar. Right? Addition is given by represented with plus and subtraction is with negative. Now, along with the addition and subtraction, vector multiplication also we have learnt, that is scalar product and vector product. Where scalar product requires your dot product and the formula is given by here cos theta AB equal to A bar dot B bar by modulus of A into modulus of B. So now to find the angle between A and B, either of the dot product or else cross product formulas we are supposed to consider. Now, if you consider scalar product, we'll be getting its value has to be a constant or a magnitude. Suppose if we consider the angle in the vector form, then we are representing it with along with the unit vectors. And after that, we have discussed position and displacement vectors. So, position vector means it is the vector which is the distance between the origin to a particular point P where it is located on the axis. And the displacement vector, it is the vector which is the distance between the two reference points. If P is located at x1, y1, z1 and Q is located at x2, y2, z2, then how we'll find the distance between two as we have seen just now. Okay. Then a second prerequisite for electromagnetic waves and transmission lines are represented with coordinate systems. What do you mean by coordinate system? So coordinate system is a curvilinear system in which all coordinate surfaces are mutually perpendicular to each other, or all the surfaces of the coordinate systems are orthogonal to each other. Orthogonal means the axis is the angle between any two axes is exactly equal to 90 degrees. Right? So coordinate system is a system that is curvilinear system and in which all the coordinate surfaces are orthogonal to each other. right? Orthogonal means 90 degrees angle between, or 90 degrees angle is separated between two axes. And there are three different cases of coordinate systems we have considered in this particular one as rectangular coordinate system, also called as Cartesian coordinate system, and second type is cylindrical coordinate system. On third one is spherical coordinate system. It is also called as polar coordinate system. And as we know that the notations or coordinate system variables are represented for the rectangular one is with x comma y comma z, and for cylindrical it is given by rho phi z, and for spherical it is r comma theta comma phi. Okay, so this is the way we can consider all the three coordinate system variables as x, y, z, rho, phi, z, and r, theta, phi, or respectively for rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. So, how in which coordinate system is suitable for in which type of examples or applications we will analyze means the choice is based upon the symmetry of the problem which we will be consider in our particular examples. So some of the examples for three types of coordinate systems are given by all the sheets are applicable for the sheets analyzing case we use rectangular coordinate system, and wires or coaxial cables case we use cylindrical coordinate system. Then for a spherical surfaces case or spheres case, we use the third type of coordinate system as spherical coordinate system. Right? So coordinate systems are the systems in which all the coordinate surfaces are orthogonal to each other. Next, coming to the representation of coordinate system variables and the ranges of the three coordinate system variables, along with that, how we'll represent the particular coordinate system unit vector representation along with the vector representations. Then we'll see the transformations from one type of coordinate system into another one. So here, firstly, the coordinate system variables are p of x comma y comma z. Means, see, if you consider here, the electromagnetic waves are to be analyzed in 3D views, that is three directional waves. Then x, y, z are given by like this. On this x-axis, if you place one cubical object and this at one particular surface, if you consider the point P is at x comma y comma z, means we don't know, means in order to find the length of this x1 or y1 or z1. So in order to find unknown variables, we are assuming it as let it be x or y or z. So we don't know how much its exact finite amount of that particular variable. That's why we are representing the ranges of the three Cartesian coordinate system variables are represented as minus infinity to infinity. Right? So this can be considered as minus infinity is less than x comma y comma z is less than plus infinity. So infinite region, these are the variables are to be vary. Hence, this Cartesian coordinate system variables are also called as spatial variables. In the space region means in the infinite region, those are the variables are ranging. Hence, minus infinity to x, y, z or ranging from plus infinity. Then, in order to represent vector form, we use the notations as vector A is the general notation for vector we have considered, and that can be written as A over bar. So this bar represents direction for that, and in the Cartesian coordinate system, as we know that the variables are x comma y comma z, then the representation for the vector is ax comma ay comma az, or sometimes ax plus ay plus az, where capital AX, AY, AZ are the magnitudes in the three directions as X, Y, Z, and small letters AX bar, AY bar, and AZ bar are the unit vectors along the X, Y, Z directions, respectively. Right? Next, second type of coordinate systems, that is called cylindrical coordinate systems. So here, cylinder means by the assumption cylinder is having some particular shape and it is having some particular finite amount of radius, and if you want to find the length of that particular arc shape, we use here curvy linear one. Hence, we are representing the rho variable, means rho is the radius of a cylinder and phi be the azimuthal angle and z be the variable which is similar to that of cylindrical coordinate systems as well as Cartesian coordinate systems. Hence, P of rho comma phi comma z, that is the case, rho is ranging from 0 to infinity and phi is ranging from 0 to 2 pi as well as z is similar to that of rectangular coordinate system, hence it is minus infinity to plus infinity, right? So if you observe here the same cubical object, if you consider and at a particular surface the point P is located and at point P the coordinate system variables are given for the cylindrical coordinate system are rho phi z. See, so if you consider xy plane here, the angle between this is represented with phi and then this particular direction, the radius from this horizon to this particular position, it is given by rho, right? So depending upon this imagination, we will write here a vector form for the first. Then we are going to write all the cylindrical coordinate system variables into Cartesian. Then Cartesian coordinate system variables are expressed in terms of rectangular coordinate systems. Okay. Then a vector A in cylindrical coordinates can be written as a rho, a phi, a z, or and a rho plus a phi plus a z. All a rho, a phi, a z are the unit vectors and a rho, a phi, a z are the magnitudes of the rho phi z directions. Then, where a rho, a phi, a z are the unit vectors along the rho phi z directions. Now, till this, what we have in the first case, x, y, z are the variables, and here it will be rho phi z are the variables. Now, depending upon this, we will write transformation formulas. One type of coordinate system variables are supposed to express in another type of coordinate system variables as x is equal to rho cos phi, y equal to rho sin phi, and z is equal to z. Now, how we have written x is equal to rho cos phi, y equal to rho sin phi, and z is equal to z means, see, consider this as a triangle. Now, here it is the length is given by x and this length is given by y. Now, from this triangle, we will be considering components as first cos phi, then sin phi. We are supposed to write the equation. Now, to find the cos phi cosine angle for this phi, then we are supposed to consider cos phi means adjacent side by hypotenuse. So, in order to write adjacent side and hypotenuse terms, then cos phi equal to, then this side is given by here phi angle, that is x by rho, right? So, here it is equal to x is equal to rho cos phi need to be obtained. Similarly, for in order to write sin phi angle, then we used to consider opposite side by hypotenuse as rho. Then from this, y is equal to rho sin phi can be written. Okay. So from this, x is equal to rho cos phi and y equal to rho sin phi we have considered. And z is the variable which is similar for the both the coordinate systems. Hence, we are representing z is equal to z only. Now, in order to transform x, y, z in terms of again rho phi z, see, rho is equal to root over x square plus y square. How we have written this? Rho equal to root of x square plus y square means, see, from this if you evaluate, x square is equal to rho square cos square phi, then y square equal to rho square sin square phi. Why? Because see, x is equal to rho cos phi and y equal to rho sin phi is to be obtained from this particular figure. So from that, by squaring on both sides, x square is equal to rho square cos square phi and y square equal to rho square sin square phi need to be written. Now by adding these two, x square plus y square equal to. Now by adding these two, rho square cos square phi plus rho square sin square phi, then if we take rho square as common, cos square phi plus sin square phi can be written. And this is the value which is equal to 1. Now from this, rho is equal to root of x square plus y square. Okay. So that can be obtained as here rho equal to root over x square plus y square. Similarly, now to write this phi equal to. So as we know that x equal to rho cos phi, y equal to rho sin phi. Now to find the ratio here, first consider y by x. Now what is y here? Rho sin phi and x is rho cos phi. So rho sin phi by rho cos phi. Okay. So rho gets cancelled. Sin phi by cos phi becomes tan phi. Then from this, phi is equal to tan inverse of y by x. Okay, this is the way phi equal to tan inverse of y by x can be obtained. Similarly, z is equal to z for the both the coordinate systems. Okay.
Like, share and subscribe. Hit the bell icon for more updates.